So today I'm going to talk about one paper was presented in CVPR last year. It's about actually phase reenactment. The idea actually is, the goal is actually if you have some source performance, actually you want this person to actually do what the target is actually doing. So from two arbitrary performance, the goal is actually to generate just some kind of reenacted sequence. So, I mean, this is kind of used in many films, like there will be like the stunt model, like the stunt actor doing some actions and which are dangerous. And then there's the main actor who just put the face, right? So now it's done actually kind of complicated way with 3D models, face scanning. So their goal is to just do it by starting from a similar sequence, just transfer this. So there will be some challenges. So for example, like the expressions and pose can be different. Timing and speech can be very different. And the result actually should be plausible. So for example, if he's doing some speech, he has to be able to actually, you have to be able to recognize that he's speaking something. So the contributions of the paper is basically, it's completely automatic. There is no anything manual needs to be done. And actually they don't require any database of anything. And finally, it's completely image based. So it can be done quite fast. So in the overview is basically, first you need to somehow track some features in both. Then using some measure, you somehow match the two faces to find which actually are close. And finally, you just transfer the face. So to do so, for example, like the face tracking, so it's non-rigid face tracking, which they track actually about 60 facial features. So actually all the details, you can find them in some previous seminar that it's stored in the web, which I did many time ago. So yeah, if you want to know how to track, just watch that video. And after that, you need to stabilize some trajectories. This method actually computes the face features for each frame. So actually, the way they do to actually smooth the trajectories is actually, first they identify some keyframes. The keyframes they are identified by actually checking where the acceleration gets to 0, or when there is some kind of change in the velocity. And then based on this, they propagate those changes in a smooth way. So basically they can remove some flickering and some strange behavior in the landmarks. So after this, they extract some feature. So first, based on the landmarks, they define four regions: 2 eyes, the mouth, and the nose. And then from these 4 regions, they extract what is called the local binary patterns. Actually, these local binary patterns is actually some kind of histogram measure on how this region looks like. So actually, just for first, if this is your region of interest, so in this case could be like some eye region. First, you divide it in some tiles. So for example, like typically 9 by 9 or 6 by 6. And then for each pixel, you replace each pixel value by one number. This number is computed this way. So if you start in one tile, in one patch, so you take the center pixel. This is the pixel you want to know the descriptor. So you compare to its neighbors, and then you just segment it based on whether it's higher or lower value. So for example, it changed to this case. For example, 4 is just the same as the center, so it's 1, it's higher, 1, 2 is smaller than 0. And then based on this, you just generate binary code. So basically starting from the corner, you can generate this sequence. So for each pixel inside this tile, you replaced by a binary, by a combination. Based on this, you can generate one histogram. So basically there will be 256 possibilities. So you just count in each tile how many of these occurrences happen. Then you attach all the histograms together, and then you have your descriptor. So this descriptor comes from many facial recognition applications. So actually it's been proved to work somehow quite well to actually encode edges and corners and these kind of things. So actually it's not part of the contribution, they just use it. Then after, in the target sequence, the first thing they do is they just cluster in time. So basically they try to put the features, either frames that actually are very similar. So once they have this segmentation, for each cluster, using these descriptors and also the landmark motion inside, so basically the trajectories of the landmarks inside the target cluster, they try to find actually in the source sequence what is the frame that match the best. So the result is basically for each cluster, we have just one source frame that actually match. And then to actually generate the motion for actually this person, what they do is somehow interpolate between each two. So what they do is actually first, so you have to consider that actually there is some landmarks here. So here you have some landmark positions, and then here are also another landmark positions. So the goal is actually to estimate the new landmark positions somehow in between these that actually minimize the following equation. So they try to actually penalize two different things. One is actually a non-rigid alignment. So they want that the new positions are very close to the original target. So for example, like this here in between there is some frame which has some landmark. This is a little bit different. So you want to somehow make that this person landmarks exactly same as this one. So that's the first term. The second term is actually try to keep the original structure as much as possible. Basically don't deform too much. So how this is done? First, the non-rigid alignment, basically they try to actually match, this is the new position. It has to somehow be similar to the 3 consecutive frames. This is done for some temporal smoothness. The second one is basically the new positions needs to be similar to actually the best match for the current cluster and also to the previous best match. And this is done by actually comparing with some kind of global affine transformation. So basically, from the neutral faces, you can compute some affine transformation that somehow encodes the transformation between one person and the other. So, with this way, you somehow try to minimize the change up to an affine transformation. After this, they extract one mask. The mask is basically computed by considering the region in which actually the landmarks are inside, plus growing the region based on some color distance. So try to keep it as, so you don't want to go outside the skin region. After this, when you have this, you have your face mask, you're actually the image, you have the new landmark positions, and then actually based on these triangulations, you can do some inverse work towards the target space. So you transfer this, and finally you can composite. So after that, you actually match the colors by solving the Poisson equation to avoid some color shifts. So here is actually the different results. If you consider only the appearance, or actually you consider the motion when clustering, and finally the resistance. So if you can see, if you just consider the landmark positions, it's actually, landmark has some noise, so it will flicker over time. So if actually you just consider the motion, then it gets better, but in some points the transitions are too big. So if you actually include the clustering, then actually the result is quite good. Finally, these are some results. So as you see, when the skin colors are more similar, then of course it works better. So actually, if you have more source results, actually the more frames you have for the source, then actually the results gets better. So here you can see actually this person didn't close the mouth completely. So actually the teeth has some problems. So the more, but for example, like this sequence has actually only 100 frames. So if you actually have a much higher amount of information for the source, then actually the results get better. Of course, if the head motion is too big, then there will be some problems too. This is actually just the same person. So if actually you try to, so this is another application. You actually film somebody, but you didn't like the performance, but actually you like the body motion. You can just shoot again just the first shot for performance, and then you can just transfer it. And then the results are actually much better. So actually this is a very quite simple paper. I mean, in terms of technically it's quite simple. There is not many amazing techniques, but the results work quite well. So there is also a continuation of this paper in SIGGRAPH 2015. I think it's not the same people, but they somehow get a lot of inspiration of this. And then they extend it to 3D by considering not only the image appearance, but they have also a depth map from the net. So in this case, the teeth or actually the head motions are actually much better because the warping is actually better. So yeah, that's basically today's seminar. So anyone, you have any question?
So if the source person is trying to follow the rotation of the target, the person is basically the problem you mentioned is solved.
It's minimized, yes. Yes. So basically, if you try to do similar, so the more similar the source and target is, actually the results are better. So one way to do this is actually you just ask the same, or actually just have a really good. So basically, the source can be anything. So it's just a. So you can ask to do more performance. So the more frames, the more different frames you have, then there will be a closer match for the target that we printed.